Welcome to this video tutorial on the optimization of a measurement setup. I don't want to teach you about the fundamentals of measurements, but to provide basic guidelines to design your tests. Let's start from some points that you cannot miss if you want to design an experimental campaign. For sure, an objective can be reached in different ways. But when you have to design experimental tests, you need to optimize resources to achieve your objectives. In particular, you have to consider time, budget, resources, and so on to perform your tests in the optimal way. You have to thoroughly consider the requirements in terms of test population, sensors and equipment, data to be collected, operational conditions and costs of your acquisitions. According to your needs from a metrological point of view, you may choose different sensors, balancing between cost and performance, presenting adequate specifications in terms of accuracy, range, and so on. Let's start from the acquisition system. At first, you have to take into account the digitalization procedure, paying attention to signal, sampling, and quantization. For the former, the Shannon theorem must be fulfilled, setting a sampling frequency higher than the double of the maximum frequency content of the signal, whereas for the latter it is fundamental to choose an appropriate full scale to optimize the resources of the system and obtain an appropriate signal resolution. Another fundamental aspect is the size of the test population. We can consider a simple equation useful when we have to compare the mean value of a certain quantity evaluated in two groups, considering a standard distribution. Statistical power, significance level, and effect size play a relevant role in this. Additionally, it is worthy to note that when you have a sample large enough, each observation added to it only marginally increases the power. You have always to optimize your resources. Then you have to consider the test environment, which is often different from the one where the equipment has been calibrated. For sure, there will be many interfering factors to be evaluated, each with a different impact on the measured data. Hence, we can perform a sensitivity analysis and focus on the factors with a greater impact to optimize the test conditions. For sure, performing repeated measurements is useful to have more robust results, sided with a rigorous analysis of the measurement uncertainty. For example, if we consider physiological signals, we can notice a plethora of artifacts and noise sources. Filtering operations are pivotal to remove noise and enhance the signal quality, thus facilitating more reliable analysis. Proper filters in terms of type, order, and frequency band must be selected to be able to extract meaningful features. Moreover, standard statistical techniques like analysis of correlation, t-test, and ANOVA can be used to analyze eventual differences between groups. Additionally, measurement uncertainty can be evaluated through comparative analysis, such as the analysis of residuals or Bland-Altman plot. Indeed, the mean value and the standard deviation of measurement differences are related to the measurement trueness and precision, respectively. Also, we can use a Monte Carlo method-based simulation to express the measurement uncertainty on the basis of a large sample, according to the Guide to the Expression of Uncertainty in Measurements. Now, let's see practical insights that we can use to optimize our results. In terms of sampling, it is usually good to go significantly beyond the double of the maximum frequency content of the signal to avoid aliasing issues and to reconstruct signals that do not mirror the original ones. Moreover, it is important to balance between time resolution and acquisition time, avoiding getting too much memory and to observe the whole phenomenon of interest. Concerning quantization, the most important aspect is to choose a proper full scale in order to avoid wasting resources and guarantee an optimal signal reconstruction with an adequate vertical resolution. To determine the minimal sample size needed for your tests, you should perform a power analysis, for example with G-Power software. You need to have a test population large enough to observe the effect of interest, but at the same time, you need to avoid too much power that would make your test results too sensitive and hence overfitted on your data. In this context, you have to select proper statistical power and significance level, usually at 95% and 5% respectively. Regarding signal processing, at first you must select proper filters to remove noise and enhance the quality of your data. The type of the filter to be chosen depends on the type of noise you want to remove, of course. Also, you can employ wavelets to remove artifacts and highlight specific components of interest. Then you can extract relevant features from your scope and compare them between groups. If you want to compare two groups in terms of mean values, you can use a t-test, whereas if you have 3 or more groups, you can opt for ANOVA. Excel, MATLAB, R, and SPSS are just a few examples of software that can be exploited for statistical analysis. Depending on the application, you may need different requirements in terms of accuracy. Comparative analyses are fundamental to evaluate measurement uncertainty and hence choose the most suitable sensor. As said before, the mean value and standard deviation of residuals are related to the measurement trueness and precision, respectively. Moreover, also outliers in the measured values can be identified. Additionally, the Bland-Altman plot allows you to evaluate the agreement between two measurement methods. Depending on your objectives, different sensors could be applied to you. If we consider physiological signals, there are a plethora of sensors available today for continuous real-time acquisition, and they can be exploited in different contexts with different requirements. Indeed, there are several application fields, from sport performance assessment to personal monitoring, through comfort assessment and applications in the context of ambient assisted living. On the other hand, multi-domain sensors enable the acquisition of many different signals at a time, like electrocardiographic, photoplethysmographic, electroencephalographic signals, and so on. Let's continue with some practical applications linked to wearable devices, both commercial and not. As said before, there is an increasing interest on multi-domain sensors. However, we should consider that usually an acquisition system has a certain sampling frequency to be divided among different acquisition channels. Sometimes we do not need all those signals, and it would be better to disable the unnecessary channels to enhance the acquisition performance on the specific channels of interest. In this slide, you can see different types of multi-domain sensors, namely the Empatica E4, a smartband from Analog Devices, and the prototype from the same producer, that enable the acquisition at least of photoplethysmographic signal, but also of blood oxygen saturation, skin temperature, electrodermal activity, electrical bioimpedance, and also signals related to movement and position. Each sensor has its own sampling frequency, range, and accuracy. Here I have reported a comparison between the technical specification of some wearable devices worn on the chest or on the wrist. In particular, we have an inertial sensor worn on a sport vest produced by the Italian company Keysport, the Zephyr cardiac belt, a smartwatch by Samsung, and a wearable prototype for the wireless measurement of electrocardiogram. Each of them has different characteristics, both in terms of functioning principles and from a measurement point of view. So let's come to the conclusions, focusing on some take-home messages. At first, when you have to design a measurement setup, you need to investigate the characteristics of your measurand, being it human subject or a phenomenon of different nature. In this way, you can optimize the choice of the sensors to be used, properly considering your resources and trying to optimize them. Hence, you have to properly set the parameters for signal digitalization. You will measure raw data to be analyzed. Filtering operations are fundamental to enhance the signal quality before extracting the features of interest for your application. In a few words, you have to optimize your resources, including equipment, time, and budget. You have to gather a proper test population and to perform measurements with sensors fulfilling your needs in terms of measurement accuracy. The acquisition phase is fundamental and has to be extremely rigorous to guarantee the quality of your data. On the other hand, you need to avoid undersampling as well as to do tests on a too small population to avoid bad quality data overfitted on your sample. Also, avoid to waste your resources and to be hasty and sloppy in performing tests. Finally, here are some references on the basis of this video tutorial. Thanks for your attention.